All right, getting into our next lesson on transformations. Here in this unit today, we're looking at rigid motion movements, and we'll talk about what that means, including slides, flipping, and spinning different images to look like different images that we can make that are new. All right, so for a warm-up here, just drawing some lines of symmetry. If it has more than one line, we can draw more than one line. So for one, I'd see a line of symmetry right down the middle, a vertical line of symmetry. For B, we'd have a horizontal line of symmetry. For 3, I see 2 lines of symmetry, both a vertical one and a horizontal line. And the same thing for number 4, the X. Vertical and horizontal. Okay, so we'll be drawing on that knowledge of lines of symmetry when we get to our various transformations we're going to look at. So again, keys today: learning goals, model transformations on a plane, translate geometric objects on a plane, reflect, rotate, and just describing single rigid motions that maps a figure onto a congruent figure. So a lot of this lesson is going to be very hands-on, using patty paper to trace figures, rotate them, slide them. I'll try to do my best I can digitally here to make an idea what you should be looking at and working with your hands with these different objects. So key terms: plane, transformation, rigid motion, pre-image, image, translation, reflection, line of reflection, rotation, center of rotation, and angle of rotation. We're going to talk about what all of those different things mean. Okay, moving on to the next page. It's kind of an intro into our transformations here. It says Kensington Middle School Track Club is holding a 5K to raise money for new uniforms. They want to create a logo for the race that includes the Running Man icon. However, they want the logo to include at least 4 copies of the Running Man. So if you have patty paper, we would trace this image onto a sheet of patty paper, and it says create a logo for the track team on another sheet of patty paper that includes the original Running Man and 3 copies. One example that's been slid to the side, one flipped, and then spinning the picture to be facing another way. So after you can trace it, you can manipulate that, spin it, slide it to get different looks at it. Just to give you an idea, to try to give you the best picture of what you'll be looking at, I kind of took some screenshots of this. Let me erase that. So like here was our original image. Now my images, because of screenshots adjustment, might change size a little bit. We're not looking at changing size. You'd have an exact image and it just spin or flip. From there, like this could be spun, it'd be a rotation, also rotation, another rotation. And sliding it, you'd keep the same orientation, but just move it from one way or the other. But again, my images here, just because how the screenshots were, are showing size changes. Again, your size is not changing. You're just taking that image you've traced and manipulating it, moving it around your paper. Okay, so what would we notice about the copies of the Running Man? So like I just mentioned, each copy, if I start my pen here, each copy would have same size and shape. They're all congruent. Remember from our last lesson, congruent just means they're equal in size and shape. That's not changing from one figure to another. So each sheet of patty paper, as you're doing this, is representing a model of a geometric plane. So all a plane is it extends indefinitely in all directions in 2 dimensions. So if you think of like a piece of paper laying on a table, if that would continue in all directions, that would be in a plane together. You could take that paper and turn it vertically, and now you have a vertical plane. But in 2 dimensions, we're just talking, like I said, a piece of paper on the table. Imagine that going in all directions, and that's in a plane. So as you slide something on that image, on that paper, left to right, you're moving it within the plane. All right, so translations is the first movement we're going to look at. Probably the simplest movement to look at. Okay, and you're going to explore different ways to change planes, figures on a plane. Transformation is the mapping or movement of a plane and all the points of a figure on a plane according to a common action or operation. Okay, and a rigid motion is a special type of transformation, with the key being it preserves the size, shape of the figure. So again, they are congruent. When you slide something, flip it, rotate it, we're not changing the size or the shape of it. All right, so it says you're going to be exploring translations on a plane using a trapezoid shown. So in the back of this lesson, if I go all the way down to it, you're going to find a page, the trapezoid like this on it. So I want you're going to be tracing that onto a sheet of patty paper. And I'll be sliding back and forth between pages here to try to let you see exactly what we should be talking about here. So it says use a translations map at the end of the lesson. That's what I was just showing you. Use a straight edge and trace the trapezoid on the shiny side of a sheet of patty paper. And then slide that patty paper containing trapezoid AB with the one segment A, the new segment AB, the new image. So we have the pre-image and then the new image. Record the location of the trapezoid ABCD on the map. This image is called trapezoid, the new image ABCD. So I'm going to go down to that page. So in other words, if you were to take this, imagine if I turn, it's going to mess up the orientation of my iPad screen here. But if you just slid that image down, I'll draw it as best as possible to be the same, you're going to get something that looks like this. So here would be our new D, here would be our new C. So that image was slid, it was translated to that location. First right, and then up from the orientation that we are currently looking at it. Okay, so we got into that. So which angle in trapezoid ABCD maps to each angle of trapezoid, the new trapezoid ABCD? The angles map to the exact angles they correspond with there. So A to our new A, B to our new B, and so on. Okay, which sides of the trapezoid correspond to the sides of our new trapezoid? Again, they're going to match up perfectly. So like AB is going to go to our new AB. Okay, what do we notice about the measure of the corresponding angles in the pre-image and the image? Again, when we are doing any of these rigid motion movements, we're not changing sizes of angles, lengths of sides, or anything like that. So they are the same. So same in both. What do we notice about the lengths of the corresponding sides? Again, same in both. Just going to keep reiterating that throughout this lesson, that we're not changing the size and shape of the figure. What do you notice about the relationship between AB and CD? So if we go back to the original, these two sides, since we're not changing the size and shape, they're going to remain parallel. So they are still parallel. And then F, is the image congruent to the pre-image? Yes. Side lengths and angles remain the same. All right, moving on to our next page here. So that type of movement on a plane containing a figure is called a translation. So a translation is a type of transformation. So it's a rigid motion transformation that slides each point of a figure the same distance and directions. Like I mentioned earlier, that one movement had a movement to the right and then a movement up vertically. So 4 says, on the mat, draw segments that connecting corresponding vertices of the pre-image and the image. So again, I'm going to go back to where I drew that here. So from the pre-image to the image of all the vertices. Okay, and what you will notice once you measure those is that they're all remaining the same. That's the key here. Get back to our appropriate page. They're all the same. So all segments are the same. Same measurement. Okay, B, compare your translation and measures work with one of your classmates. So someone sitting next to you, see what they got. Should be the same thing. They might have moved it to, maybe they chose a different spot to move it if they translate it, but both should have segments that are equal. Now, again, not your segments are equal to their segments, but all of their segments are equal, all of your segments are equal, because you have translated it, each vertice, the same distance. Okay, 5, consider the translation we just created, as well as your classmate's translation that you just checked with, who you're working with. What changes about figure after a translation? So all that changes is the location in the plane. The orientation of it is not changing, it's not spinning or anything like that, just the location. So what stays the same? I just kind of gave you the answer to that. The orientation and the size. So it's not facing a different direction. It is just slid, either horizontally or vertically. What information do you need to know to perform a translation? You need to know the direction and distance to translate. All right, so let's move on to our next transformation. So it says the first transformation we explored was a translation. Now let's see what happens when we flip it, or better known as reflecting. So when you say flip, what we are doing is we are reflecting it. So again, take that trapezoid that you've traced on a sheet of patty paper, maybe trace it again, and then fold that patty paper in half and trace the trapezoid on the other half of the patty paper. And then open up your patty paper so you can look at the two images. So for instance, if here was my original, if I folded it, I might get something that looks about like that. So when you're looking at what you traced, that should be about what we're looking at. So making conjecture about how the image and pre-image will be alike. Again, varying answers here. One thing key is we're not changing size or shape still. So there's still equal side lengths, equal angles. All right, moving down to 2, it says align the trapezoid on the patty paper with the trapezoid on the reflections map. Fold the patty paper along one line, trace the trapezoid on the other side of the crease, and transfer onto the reflections map. Label the vertices of the new A, B, C, D of the new image. Okay, compare the pre-image and the image you created. So again, I'm going to go down, look at this page, and I'm going to say, let's see if I have a better one to work with here. Here we go. And I'm going to say if I folded it, I know it's going to speak about each line individually, but I'm going to say if I folded it across line L3 here, I would get an image over here that looks about like so. Again, much easier when you manipulate this with patty paper in front of you, but I'm going to try to draw it in there as best as possible so you can see what we're talking about. All right, so going back to that page, keeping that in mind. Okay, what do we notice about the measure of the corresponding angles on the pre-image and the image? Again, if we're doing rigid motion transformations today, none of our corresponding angles are changing. Side lengths aren't changing, angles aren't changing. So that's our answer to A and B here. They're all the same for both. So we haven't changed any of the angles, we haven't changed any of the side lengths. We're just flipping it, reflecting it across that line of symmetry. All right, moving on to the next page. What do you notice about the relationship between AB and CD? Again, if I go back to our original image here, if we're not changing the size and shape of the figure, AB and CD are still going to be parallel. That is not changing. So they are still parallel. Okay, is the image congruent to the pre-image? Yes. Again, we are not changing angles or side lengths. So no angle or side length changes. Okay, draw segments connecting corresponding vertices of the pre-image and the image. Measure the lengths of those segments and distance from each vertice from the fold, so not to each other, from the fold, and what do we notice? So in other words, I'm going to go down to that image. If I were to measure this line to that vertice A, new A here, and go to the original A, those would be the same. If I was to measure from vertice D to the line of reflection, we'll pretend that's straight, those are going to be the same. Make that a little prettier, erase this little stray mark here. Okay, so key being, I'll draw one more. We'll go B to B, B to B here. So the distance from the line of reflection for each vertice is the same from the pre-image to the new image. So that's our key here. We'll go fill that in. So distance from vertices to reflection line are equal. We'll say in pre-image and new image. Pre-image and new image. Therefore, repeat the reflection investigation and fold along line 2. We just did line 3. Record your observations. Same thing with line 3 down there at the bottom. What you're going to find on all of them is the same as above. No matter which line we reflect it over, you're going to find that distance from the corresponding vertices to that line of reflection is the same. And again, makes sense because we're talking about reflecting it over an axis, which means it's going to remain symmetrical. And symmetrical means we're going to be equal on each side of that line of reflection. Okay, so again, that type of movement is a reflection. Also might easily simply call it a flip. So simply what a reflection is doing. And a line of reflection is a line that acts as a mirror, so the corresponding points are the same distance from that line. So 6, what changes about the figure after the reflection? Well, it's flipping over, so the orientation is changing. And when you think of, say, your reflection in a mirror, when you hold up your right hand, it looks like your reflection in the mirror is holding up their left hand. So the orientation has been flipped around. It's the same concept here. We're just dealing with images on paper, and that line of reflection on the paper is essentially our mirror. So what stays the same about the figure after the reflection? Again, just like before, since they're staying same angles and side lengths. And what information do we need to know to perform a reflection? You need to know the line of reflection. All right. Next one we're going to get into, I think it's probably the most challenging one, is rotations. So it says now you've investigated translating and reflecting a trapezoid on the plane. Let's see what happens when you spin or rotate the trapezoid. So we're going to use that rotations map at the end with your patty paper that you're manipulating. Again, I'll try to do my best to kind of draw it in here so you can see what we're looking at. So again, trace that trapezoid onto the center of a sheet of patty paper and imagine spinning the patty paper so that the trapezoid is no longer aligned with the trapezoid on the map. Okay, so one there, make a conjecture about how the image and pre-image will be alike. So again, all this question is trying to reiterate to you that any of these rigid motion transformations is it's going to have same side links, and angles. Okay, as we move on to the next page, align your trapezoid with the trapezoid on the rotations map. Put your pencil on point O and spin the patty paper 90 degrees in a clockwise direction. So I'm going to go back to the page you should be working on. And it's talking about putting it on one of these points. Let's say, as you traced it, stick your pin right there on your patty paper, and you're going to then spin your paper one direction or the other. Okay, so that is we're rotating around that point. So put your pencil on point O, like I just mentioned, spin it 90 degrees in a clockwise direction. I think the arrow I just drew would be counterclockwise. So go back, and I just drew pointed one of them, but we're going to go in a clockwise direction. So we're talking about to the right, essentially, if you want to think of it that way. Okay, then compare the pre-image and the image of the rotation. So for A, it says, what do you notice about the measure of the corresponding angles? Again, they are the same because we're not changing that. Same with B, what do you notice about the lengths of the corresponding sides? Those are the same. What do you notice about the relationship from AB to CD? Again, going back to our original image, A, B, and CD, since we're not changing angles or side lengths, those are going to remain parallel. So they're still parallel. And then D, is the image congruent to the pre-image? Yes. So we're still maintaining that congruency because we're not changing the side lengths and the angles, the angle measurements. Okay, for 4, take your patty paper, draw 2 segments, one to connect point O to A, and another to connect point O1 to the new A. Measure the lengths of these segments. What do you notice? So again, I'm going to go back and try my best to draw it in here. And again, we said clockwise, so I'm going to erase that arrow. So if you were to rotate this clockwise 90 degrees, essentially it's going to look something like this when you get it over here. Okay, so point being, and mine's probably the distance is not quite right, but we'll mark it off. If you measure your corresponding distances from vertices, corresponding vertices to that point of rotation, here's our A, here's our new A, you're going to find that is the same measurement. Okay, in other words, look at a different segment here. So D, and again, this is off, but we'll imagine it looks right. Again, much easier if you're manipulating this by hand. These two would be the same. So the corresponding vertices will have the same distance to the origin. We'll fill that in. So corresponding vertices will have same distance to the origin. Okay, the measure of the angle formed by the segments. What do we notice about that? Okay, if we rotated it exactly 90 degrees and you measure those the line segments, it should measure 90 degrees. So again, in other words, if I go back here, we use green to match up these two line segments to the corresponding vertices. If we rotate it 90 degrees, it should be a 90-degree measurement. All right, moving on to the next page. repeat that process for the previous question with point B and your new image point B. What do you notice? So just write in same as above. So every corresponding vertice should have the same distance. Same with 6 for point C and point D. So all the corresponding vertices should have the same distance of measure to that point of rotation, and they should form that 90-degree angle between those two lines. All right, question 7, repeat the rotations paper in a 90-degree counterclockwise motions. Record your observations. Again, all those observations, no matter which direction or angle we rotate it at, they're the same. All that's changing is your angle of rotation and the orientation of that figure as it rotates around. So that distance, no matter where we rotate it to, from a vertice, corresponding vertice, back to that point of rotation, will always be equal to each other. Okay, again, same with 8, same as above. All that is reiterating that no matter what angle of rotation we use, you're going to find that those same things have in common. The distance from the corresponding vertices to the point of rotation is going to remain the same. All right, so this type of movement in a plane, like we've been talking about, is called a rotation. Been saying it over and over again. Okay, it's moving around a fixed point called the center of rotation through a given angle called the angle of rotation. Okay, the center of rotation can be a point outside the figure, inside the figure, or anywhere on the figure. The point of rotation could be anywhere. So 9, consider the rotation that we just created. Describe the centers of rotation used for each investigation. So, for example, we used point 01 and rotated 90 degrees on that first example. Okay, B, how do you identify the angle of rotation, including the direction in your patty paper rotations? By measuring the angle of the segments connecting corresponding vertices to point of rotation. Okay, so in other words, I'm going to go back to that image at the end. We measured the angle of rotation by measuring, I'm going to circle it in green because I have it in green here, by measuring that angle of the segments connecting the point of rotation with the corresponding vertices. In this case, with the green one, it was D, corresponding point D. Okay, C, what changes about a figure after a rotation? Well, what changes is the location in the plane.
As an object rotates, it's oriented.
Siri's listening to me. Location in the plane. What stays the same about the figure? Again, corresponding or congruent figure still, so what stays the same is the angle measures and side lengths. What information do you need to perform a rotation? The angle of rotation, and the center of rotation point. So what point are we rotating around? All right, then the next activity is going to be exploring with different objects again. Again, you're going to use your patty paper to construct all these. I'll kind of talk through what we should end up with results looking like here. So it says, first one, rotate Allie the alien 180 degrees. Be sure to identify your center of rotation. Well, if we rotated 180 degrees, it essentially will flip all the way over. And what you're going to end up looking like is basically the same figure in the same spot, because this figure is symmetrical in that direction. So that you should end up something like that. Again, try that on your own. Make sure you can match that up. Make sure it looks the same. 2, translate the googly eyes horizontally to the right. So remember, a translation is just a slide. So if you were to trace these and just slide them to the right, should look pretty much similar. Again, I'll try to draw in what it's going to look like. Should look something like that. It is slid to the right. It hasn't flipped, so the eyes aren't looking in a new direction. It's just slid over. All right, if you were to rotate E 90 degrees clockwise, okay, again, tracing your patty paper, rotate it, you should end up with something that looks like, let me go back, it's the same length. I'll do my best to draw it, but again, trace it and rotate it. Should end up something that looks like that. It is rotated 90 degrees. I'll call that my point of rotation, just for approximation. Okay, 4, transferring the running man so that he's running in the opposite direction. So again, this would be a flip. So if you imagine a reflection line, if I took that and drew a line right there and folded that over, you would create an image that looks like he is running to the right. It'd be an exact reflection across that line of reflection. All right, again, take each one of those, manipulate it with your patty paper, make sure we're understanding those rotations. All right, and to finish up here, where it says talk the talk, congruence in motion, describe transformation that maps one figure onto the other for each one of these. So figure A to figure B, that has been translated. It's been slid up and right to get to figure B. Okay, figure A to figure C. If you look at that, that looks like we'd have had a reflection. It's been flipped across that line, so reflected. It's reflected over that line of symmetry. Figure A to figure E. Okay, so to get to figure A to figure E, they're both facing in the same orientation, so it's not reflected. That has been rotated. If we call it like a point of rotation here, that's been rotated counterclockwise, and it looks to be about 90 degrees. We'll just estimate. So rotated 90 degrees counterclockwise. Let's put counterclock. And figure D, for letter D, figure C onto figure D. So if we're looking at figure C to D, again, we got another reflection. They're a mirrored image. Again, this vertice, if we were to flip that to our line of reflection of each, would be the same. So that is a reflection. All right, and then number 2, explain what you know about the image that results from translating, reflecting, rotating the same pre-image. Again, I would just add to it that all remain same sides and angle measures. So same size and angles, I'll put it. Okay, they'll be congruent. Okay, with 3, figure A is congruent to figure C. If you look at those two, and figure C is congruent to D, answer each question. So what is true about the relationship of figure A and D? So again, this is a concept that if A is equal to C and C is equal to D, what that means is A has to be equal to D. So they must also be congruent. And from B, how could you use multiple transformations to map figure A onto figure D? So A to D. So we got, we can do it by one transformation if we just did a 180-degree rotation that direction. That would be probably the easiest way to get to figure D without doing multiple changes. So rotated 180 degrees. And when you're talking about 180 degrees, that's completely all the way around, halfway all the way around. So it doesn't matter if we move clockwise or counterclockwise, 180 degree rotation is going to be the same. All right, so that finishes up this lesson on rigid motion transformations. Again, encourage you to use your patty paper to manipulate these things, look at all the images, see what the pre-image, post-images look like so you can hands-on experience these different things.